Introducing the MP80 Mark I breadboard computer project. Hello, I am the Mighty Pez. In the first of a 2-video series, I will be demonstrating the MP80 Mark I, my Z80 breadboard computer project. So please, join me. This little tangle of wires and blinking lights is the result of a project that I've been working on now for several months. It's a project that's been near and dear to my heart, and it's called the MP Mark I computer. It is a Z80 CPU based computer, very minimal functionality that I've been working on as part of a project. I will share some of the motivations behind this project. I first became aware of and interested in computers from the 1970 edition of the World Book Encyclopedia. My parents purchased the set for my sister and I used to take each book back to my room to read. Once I got to book C and read the article for computer, the seeds were planted. Although at that time, the thought that I would ever come in contact with the rare room-sized behemoths were unrealistic. However, while visiting the Baltimore Science Center in 1977, I first accessed a green screen terminal attached to a mainframe and played a text-based version of Lunar Lander. I was hooked. Little did I know that personal microcomputers from Apple, Commodore, Atari, and Sinclair, to name a few, were already coming into being. In 1980, my dad purchased our first computer, an Atari 400. Mind you, we couldn't afford the tape drive, so every night my sister and I would alternate typing programs into the computer for magazines, play them until we had to go to bed, then power off the computer, losing everything, only to restart the cycle again the next day. Over the next several years, I owned a succession of 6502 and 68000 based computers before owning my first PC. I never had the opportunity to work with a Z80 CPU based system. Finally, in 1986, while studying computer science, I took a class called Computer Logic and Organization, where we built a 4-bit CPU from logic gates. And at that time, I became enthralled with digital integrated circuits and logic. However, due to the demands of post-school jobs, life, and family, I was unable for decades to pursue my dream, which was to build a computer from integrated circuits from the ground up, like Steve Wozniak did. But now, as my career reaches the final stretch, and my passion for older systems is still alive, I've restarted the journey that I began years ago. Here are a couple of my guiding principles. First, my number one focus is on self-improvement and learning. A focus on basic principles of system design using discrete circuits versus assembled system-on-a-chip or microcontrollers. A focus on classic hardware, such as the Z80. As a note, my interests are not in retro computers. My interests are in computers. But like my favorite bands became classic rockers, my computers became retro. Limit my design to what I am capable of understanding. I will only copy and reuse what I can understand. It is not intended to be a minimal computer. It is not intended to be an optimal computer. And most importantly, any rule that gets in the way of learning goes out the window. Other than principle number one, anything that blocks learning and progress is an artificial roadblock. So let me share some of the features of the MP80 Mark I. An incredibly fast 1 Hz CPU clock. It is Z80 CPU based. Don't worry about Terminator code running on this system. 32,000 bytes of RAM. Who could possibly need more? The ability to load and execute a 256-byte program into memory. Blinking lights to impress friends and family. No pesky I/O devices to store programs on. If code was worth entering by hand, it is worth re-entering by hand. No ROM. No operating system means nothing to patch for vulnerabilities. No monitor program No software compatibility issues, as there is no software compatible with any other system. Breadboard design means that if my cats decide to help, my project may be done. So let me provide a brief overview of my breadboard computer project. Starting with the bottom part of the breadboard, you'll notice that we are powered by a USB port. The USB port only provides power to the board. It is not used at all for any communication at this time. That will be left for a future endeavor. Next, I'm going to go up to the quote-unquote front panel, which is obviously in the rear of the breadboard. It supports 3 different modes. The store and exam mode for memory. It controls whether, when I'm in manual mode, if I'm writing to or reading from memory. CPU in manual mode. That allows us to manually operate memory or have the CPU control memory. And the third mode is automatic and manual clock. So right now, this would be the clock line. It is not blinking. It is not synchronized to the automatic clock, so it means it's in manual mode. We're going to flip it into automatic mode. And you can see it is now paired with the automatic clock. In manual mode, the clock would be triggered by hand. So if for debugging reasons I want to step through processes on the Z80, I would put it in manual mode and single step the clock. But normally we'll be running in automatic mode, which is running at a whopping 1 Hertz. Okay, so right now, let me go into this portion of the breadboard. This is our memory entry area. It is a register built on 74HCT74D flip-flops, and it is used to control a memory register that we use to store 1 byte at a time into memory. So we can program in the binary bits that we want to store in memory, and then we do a load and increment, and it will load that into memory, increment the address, and allow us to store more data into memory. Right now I'm in exam mode, so I will be demonstrating this in a moment. Next, we'll go up to the clock board. As I've already explained, there is a manual single trigger and an automatic clock. I also have support for 1 megahertz clock, but I'm not yet ready to wire that in and run it at a fast speed. Up here we have 2 logic chips, HCT04 inverter and a 74HCT32 OR gate. And these are used by the front panel switches to control different buffers that I will be touching on in a minute here. So on the right side of the board, this is part of the controller for loading data manually into memory. Again, the 2 octal buffers here allow us to not conflict on the bus. Either the CPU or the front panel will allow us to access the data and memory bus without conflicting with each other. At any given time, only one device can write to memory, and we control that again through the switches up here. There's an address reset button that will clear out the current memory address, allow us to start entering data into memory, and then increment and move on. I forgot to point out that this button is the load increment. It will take the current data that's in the register, load it into memory, and then it will increment the address counter by 1. So you can see we load data, load increment, and it moves the address counter up by 1. This is the bus area of the board. There's the data bus in brown, 8-bit data bus, and a 16-bit address bus in blue. Our manual entry plugs into the address bus, to the data and address bus. The memory chip plugs into the data and address bus, and the Z80 CPU plugs into the data and address bus. And each one of those are controlled so they all can't be reading or writing at the same time. Over here are just some debug logic lights, LEDs, that I've added so I can tell when output is enabled, chip enabled, or write is enabled. These are all inverted. You may be able to see the little over mark. That means it is active low. So when this light is out, it means the chip is enabled. Output enabled is currently lit, so that means the output is not enabled. Write enable is also currently enabled because it is in the low state. So the bar over that input pin means that it's active when it is in a low state. Same up here with the CPU being in reset or halt mode. The red light enabled means that it is not halt. Sorry, the red light means it's disabled and not in halt mode. Reset, however, is currently enabled, so the Z80 CPU is not active and cannot write to the data or memory bus. If we flip the switch into CPU mode, then reset now high means that it is not in a reset mode. So we're going to leave it in store mode. Again, over here at HCT08, this is an AND chip, and this allows us to use both the switch and the Z80, which both have write enable and output enable pins to control the memory chip without conflicting with each other. So we take the signal from the front panel and the signal from the Z80 CPU, and them together, and that becomes the control line for the memory chip. In a nutshell, that is the architecture of the board. So a quick demo, we are going to load the world's smallest program into memory. It is simply going to be a jump at address 0 back to address 0. A Z80 jump is a 2-byte instruction. So we're going to make sure that we're in store mode. The CPU is in manual, so the CPU is not controlling memory, but the front panel is controlling memory. We're going to leave it in auto clock. The Z80 CPU needs to have several clock cycles while in reset mode to clear out all of the registers and control lines. So obviously it's been blinking for a while, so the Z80 CPU is reset and we'll be ready to run when we're ready for it. So we're going to reset the address line, and we're going to go ahead and enter the 2 bytes, C3 and 00. So let's enter Charlie 3 in binary. And then we will also load the 00 in binary. And I'll add a couple extra zeros, no ops, which are not needed. In fact, they won't even be touched, but I kind of add a couple extra zeros to clear out memory at the tail end of the program. So we've now loaded our 1-line program into memory. We're going to put it in CPU mode. It clears out the address line, and at this point in time, the Z80 is going to take over. And what you'll see is every time it goes through the loop, you will see the Charlie 3 in binary show back up, and then it'll loop around again to address 0. There you can see the Charlie 3 again. And if you're paying attention to the clock light, you can see that it actually takes multiple clock triggers for each instruction. So right now the CPU is an infinite loop. All we're going to do is continue to read the jump to address 0 line in memory and keep jumping back to address 0 and rereading and rerunning that instruction over and over. So that is an example of the Z80 CPU running. I'll go ahead and put it in manual clock and show you that it's the same function, except I'll be running that manually. And there you go again. There's the jump to address 0. And again, the jump to address 0. And we start over and over. And that is the architecture of my simple Z80 motherboard. I will have a further follow-up video where I go into more detail about manually writing an assembler program and converting the opcodes by hand. And it'll be a slightly more detailed loop in that video. Thank you for watching. I hope this video has been informative and enjoyable.